Okay, so this is the BASE experiment at the anti-proton decelerator facility of CERN. BASE is designed to compare the fundamental properties of protons and antiprotons, such as the charge-to-mass ratio, magnetic moments, and so on and so forth, with ultra-high precision. In order to do this, we are investigating the properties of single particles, so single trapped antiprotons, which are oscillating in a device which is called a penning trap. The detection of single trapped antiprotons requires the utilization of ultra-sensitive superconducting detection systems. And recently we've realized that these detection systems are so sensitive they cannot only be used to study the properties of protons and antiprotons, they can also use to maybe detect other particles. Then there is an effect which is called the inverse Primakov effect, and this effect converts basically axions and axion-like particles in strong magnetic fields to radio frequency photons. So if such an axion exists with in a certain mass range and we have conversions of axions to photons, our sensitive single antiproton detectors could pick these signals up. So that's the basic idea. And what we've then basically done, I mean, this year's the spectrum analyzer. At the moment we don't have signal, but this year's the spectrum analyzer, which is basically used as a measurement device for signals which are induced by axion-like particles. So on this spectrum analyzer we would see some peaks if there would be a signal. And what we have done is that we've basically studied the residuals of our single particle spectra, and we're looking for exotic signals, exotic small peaks which are not understood. And these exotic small peaks, they would be signatures for axion to photon conversion if they exist. So we have not detected anything, but we've reached with this study limits in a very small mass range at around 9 nanoelectron volts, a sensitivity, a limit sensitivity on the conversion of axions to photons, which is comparable to limits which are derived from astrophysical studies and satellite experiments. The nice thing here is that this has been done with a penning trap experiment, which is not purpose-built for axion search. If we would use the technology which we have and project this basically to a purpose-built axion telescope, if you like, then we could improve the experimental sensitivity by order a factor of 100 and the detection bandwidth by order a factor of 3000, and we are considering to do this.
Big Bang should have generated equal amounts of matter and antimatter, which are twins but with an opposite charge. Put the two together and both are annihilated, yet somehow the universe is still here. Why haven't antimatter and matter destroyed each other by now? Antimatter can be contained by strong electrical and magnetic fields in a penning trap, which sounds like this.